Hello, this is Jack Jackson. In this section, we will be developing a method for finding an appropriate sample size for a t-interval given a margin of error and level of confidence. So let's start by recalling for a z-interval, we can first determine the sample size needed for predetermined values for level of confidence, 1 minus alpha, and a margin of error e using the following formula. Section 4.3.3 in this playlist, or in these slides, goes over how we got this formula and using it. But it's a basic little formula. It's the same formula used to find the margin of error to compute a confidence interval for a z-interval, except it's now solved for n instead of e. So we get n on this side by itself, and the formula is inverse norm of 1 plus confidence level divided by 2, 0, 1, so a standard inverse normal, times the population standard deviation, sigma of x's, or just sigma, divided by the margin of error e, and then square the whole thing, and remember that we always round up to a whole number, never round down. Well, that works pretty nicely. So it's not too hard in a way to change this formula to work for an inverse, for t-distribution, and do the same formula, or corresponding formula. The sigma then is just replaced by s, and the inverse norm is replaced by inverse t, and we get this problem. However, we run into a wrinkle here. This is not really solved for n, because there is n alone on the left side, but there's still an n on the right side. We need to know the n to find the degrees of freedom to be able to calculate the inverse t, and that gives us a bit of a problem. So I'm going to show you an iterative technique that I'm going to use, a kind of a couple-step technique that's going to allow us to get a reasonable estimate for what we need for n for a t interval in the next few slides. So what we're going to do is, just as determining a sample size for a z-interval, we're given a maximum acceptable margin of error, e, and a desired confidence level, 1 minus alpha, or CL. And for example, let's suppose we want the following. We want a margin of error of up to 15, a confidence level of at least 90%, 0.9. From this, we can calculate, of course, 1 minus alpha over 2, or in other words, 1 plus confidence level over 2, is 0.95. So what we want to do is pretend that we're finding a sample size for a z-interval to get a first estimate for n. Then we'll use this value for n. We can use the formula for a t-interval to get our final estimate for n. So sort of a two-stage process. So far, we have the margin of error is 15. Our desirable confidence level is the 1 minus alpha over 2, or 1 plus confidence level over 2, is 0.95. So we have to have some way to estimate the standard deviation to do the to replace this for sigma here, and what we'll do, of course, is just use s there. Or if we have some historical data that gives us a better estimate or a reasonable estimate of the standard deviation, we could use that. But either way, we use this in place of sigma. Now, if we haven't done, what if we've got a sample already, we could use the standard deviation from that little pilot sample here, or we might have some idea in the past, but we're going to have some idea of what to put in for this. Okay, so let's suppose for this example we do this one way or the other and estimate sigma is 25. So we could go ahead and put that in here as 25, 0.95 for 1 minus alpha over 2, that's 1 plus confidence level divided by 2. Work this out and we get 7.5, round up, that's 8. Or round off. It could actually be rounded off, and that's reasonable enough to use to start with. So round that off, that's 8. So now we can do, you can see that calculation done on the calculator here. Now with that number in hand, let's go back to this formula here. Margin of error is 15, 1 minus alpha over 2 is 0.95, s is 25, and n1 is 8. Plug in this formula right here to put in s, the margin of error, and n minus 1, that's 8 minus 1 is 7. do that inverse t, square that, the whole thing here, it's about 9.97, always round up this time, and so we get n equals 10, and that's going to be a reasonable first estimate. Now, there are a couple of things to work with this. If this is less than 30, then you also need to know that your distribution of individuals is at least not too far off of a normal distribution, so the distribution of sample means will be approximately normal, or this t-test or t-interval doesn't even work. Unfortunately, this does require us to know S, which is a sample standard deviation, or we could use some historical approximation there. So this would require us to do a sample first, maybe a pilot sample, and see if that works. Okay, so anyway, we get this, we want to have this situation. So we can check to see that this inequality is actually satisfied by this particular method. So we decided we need to get a minimum sample size of 10, and recall that we want n to be greater than or equal to inverse t of 1 minus alpha over 2, n minus 1 degrees of freedom. S is here, E is here, square it. We need n to be bigger than that. We work it out. So here I just plug this in, inverse t of 0.95, n minus 1, 25, 15, square it, and so forth. Look at the table, and notice that 10, if we go to, so the first time x surpasses 10 is an n of, let's see, the x first passes y1. That's what we want. We want x to be bigger than what y1 is. And the first time that happens is at 10 right here. 8 and 9 are too small. 10 is the first time that happens. So 10 will be the smallest one that will produce the desired level of confidence and margin of error, assuming that our sample has a standard deviation of 25 and our margin of error is 15 and our confidence level was 90%. Okay, so the sample size generated by this technique here should produce a confidence interval with the desired level of confidence and margin of error, or better, if two conditions are met. The distribution of sample means is approximated well by normal distribution, number one, and number two, the sample standard deviation of the sample we take does not exceed the estimate we use for S in our computations. If we know that the distribution of individual values is close to normal, then a relatively small sample size, like the 10 we have here, produced by this method would be sufficient. On the other hand, if we are not sure the distribution of individuals is nearly normal, we can just use a sample size of at least, say, 31 to satisfy the normality constraint. So in practice, it's not too problematic to just use a minimum sample size of, let's say, 30 if this procedure produces a smaller result. If the sample turns out to have a higher standard deviation than our estimate, then our sample size could be a bit low. So overestimating S in this calculation and or adding a few to the sample size generated by this technique will give us a safer value of n. So it's a little bit of a complicated two-step technique, but at least it does kind of work. Okay, so I actually was able to program this into a TI-84 calculator. So here's some screenshots for a TI-84 program. If you can get to the UAFS campus and see me, I can transfer this program to your calculator directly. Anybody that comes by, I'll do that for you. Otherwise, you can program this program in using these screens here. I call this, the name of the program is N for CI4MU, or the sample size N for a confidence interval for mu. In other words, for a T interval. Or for, this one actually does it whether it's a Z interval or a T interval. It does both at once. So this actually will solve the sample size problems for a Z interval as well. So you can see kind of how I've got this program set up, and it asks puts some text on there and tells you what it's about, Then it's going to ask you to prompt you for the confidence level C and the margin of error E. Then it has a menu that you choose either the standard deviation of the population is known or unknown. If it's known, it will skip down to part 2. We'll do that in a minute. If it's unknown, it'll stay here in 1. If it's known, it'll skip down to part 2. The unknown part, we have to give it an estimate for the population standard deviation, which is S. Again, that could come from some historical data, or that could come from some sample, pilot sample that we've done. It goes through a loop here, which takes you through that process that we just did, and it's going to ultimately return the answer. If the population standard deviation is known, basically the first step of this process is all that matters. It's going to, this here, when you round this way, this allows you to always makes it round up. And then if the number turns out to be less than 30, then it puts a little message that says, okay, if the data is approximately normal, this works, otherwise bump it up to 30. So here, let's run the program. We're going to use the program to find the sample size needed for a t-interval for the population mean where the population standard deviation is unknown but is approximated by 10. We want a 95% confidence level and a margin of error no larger than 3. So we run our program. It says computes the minimum sample size for confidence interval for mu, asks for the confidence level C is 0.95. Then it asks for the margin of error E is 3. Gives you this menu, known or unknown. We choose unknown. And then it produces the answer. The estimate for the population standard deviation is 10. The minimum standard deviation is 10. The minimum N is 46, and it says done. So you should be able to check your calculator program against this one right here, see if it works right, and then you could go back to my earlier slides or not either the slides or the video that I did earlier and work out the answers to previous problems on a Z interval and Z interval and a T interval approximating the sample size, because this will do both. In my particular probability stat class, the students will have one bonus tutorial question covering finding a minimal needed sample size for a t-interval on the homework set 4, but there will be no such questions on the practice test or exams, so you can consider this particular section bonus material, and you can consider problem 27 on homework set 6, at least this semester. That's going to be a bonus problem. Now, at this point, we've covered enough about t-intervals that I think you should go to your textbook and read the section on that in your textbook. Our particular textbook this semester, this is section 8.3. That might change if we change textbooks in the future, but that's what we have right now.